This is page 242. We're going to do most of this page, if not all of it. We'll check it out and see how long it takes. 43 reads, which power can you write to represent the volume of the cube shown? Write the power as an expression with a base and an exponent, and then find the volume of the cube. First things first, how do you find the volume of a cube? The volume of a cube, or the volume of any prism like this, is found by doing the length times the width times the height. Now, definition of a cube means that all of these distances, 1/3, are the same. So the length is 1/3. This distance right here, so I'm going to call this the length. From here to there, that's a distance of 1/3. From here to there, that's a distance of 1/3, 1/3 of an inch. And the height from there to there, that's a distance of 1/3. So I'm going to go ahead and rewrite that, make it just a tiny bit neater. So this is 1/3, this is 1/3, and this is 1/3. And they're all 1/3 of an inch. So if I go and actually replace the length, the width, and the height with 1/3, it's going to look like this. The volume would be 1/3 times 1/3 times 1/3. Now I need to erase all that because I need to write a couple things. One thing I need to write is the power problem. Well, what is 1/3 times 1/3 times 1/3 3 times? Well, it's just 1/3 to the third power. So the power looks like this: 1/3 in parentheses to the third power. And then to solve it, it actually means what I showed you: 1/3 times 1/3 times 1/3. And this is a lot easier than it looks. It might look confusing to you, but if you multiply fractions, you just multiply all the top terms. 1 times 1 times 1, that's 1. And 3 times 3 is 9, times another 3 is 27. It's 1/27th of a, and then what we do is we label it in inches, and it's three-dimensional figure, so it's to the third power. So our two main answers here are, I'll kind of maybe put them box them here. It's this one, 1/3 to the third power, and it's 1/27th of an inch. This middle part is where I just showed my work. All right, let's move on. Number 44 reads, write a power represented with a positive base and a positive exponent whose value is less than the base. So how can I write something like this, where I've got a base, I've got an exponent, and my value here, my answer, has to be less than the base? Now you might think that's impossible. Like, even if I pick little numbers here, 2 to the second power is 4. If I tried 3 to the second power, it would be 3 to the second power, that'd be 9. How can I do that? Well, there is one kind of number that when you multiply it actually gets smaller, and it's going to be by a decimal or a fraction. For example, let's pretend I put in here 0.3, and I'm just going to do 0.3 to the second power. What is 0.3 to the second power? Well, 0.3 times 0.3 equals, 3 times 3 is 9, but it's not going to be 0.9. It's going to be 1, 2, I'm going to move the decimal over 1, 2 spots. It's going to be I'm going to put actually a 0 there. It's going to be 0.09. Now some kids would say, well, 9 is bigger than 3. Yeah, but this is 3/10. This is 3 out of 10. 3/10 is much greater than 9/100. This is much smaller. So the conclusion we're trying to draw here is that to get a base with a smaller value, to get an answer with a smaller value than the base, this number right here that we chose needs to be a fraction or a decimal. I know that one was tricky. You're welcome to share my answer with me, number 44. Let's go ahead and move on. Sometimes we skip the hot problems because they're either too hard or they're not great questions, but these aren't too hard, so I'm going to help you with them. Number 45 reads, communicate mathematical ideas. What is the value of 1 raised to the power of any exponent? What is the value of 0 raised to the power of any non-negative, non-zero exponent? Explain. Well, what is 1 raised to any power? 1 to the 7th, or 1 to the 5th, or 1 squared. What do we get every time? Well, this one means 1 times 1 7 times. Well, it's 1 times 1 times 1. It's 1. What's 1 times 1 5 times? It's 1. What's 1 times 2? Twice. It's 1. What's 1 to the raised to the power of any number? It's 1. I'm going to write that in a sentence. I'm probably going to type that one actually. 1 raised to any power is 1 because 1 times itself any number of times is equal to 1. Now that's the first half of the question. We're going to go ahead and do a second answer. We answered the first one. Now we've got to, here's what, I'll highlight what we've answered so far. We've answered this one. The value of 1 raised to the power of any exponent, it's 1. What is the value of 0 raised to anything? Let's go over here. What is 0 raised to any number? 0 to the first power, or 0 to the third power, or 0 to the 15th power? Well, we actually saw this on a previous page. I'm going to scroll back to it. I'm going to look back to it in my teacher key. It's actually only 2 pages back. It's on page 239. I'm going to scroll back to it. Page 239. I'm going to show you the what we learned about property of 0 as an exponent. The value of any non-zero number raised to the power of 0 is, oh, that's not the right value. That's not the right one. I think I'm misreading the question, so I'm going to go back. Yep, I'm misreading the question. I was thinking about this was saying 0 as an exponent, but it's not. This is saying 0 as the base. So let's go ahead and just go through and solve these. What's 0 to the first power? That means 0. What's 0 times itself 3 times? 0. What is 0 times itself 15 times? 0. 0 times anything is 0. So what we can say here, here's our conclusion. 0 raised to any power is 0 because 0 times itself any number of times equals 0. All right. So when 1's the base, the total product will be 1, and when 0 is the base, the total product will be 0. All right, let's move on. Let's check out 46. 46 reads, look for a pattern. Find the values of the powers in the following pattern: 10 to the first, 10 to the second, 10 to the third. What is 10 to the first? 10 to the first is 10. What's 10 to the second? Well, 10 to the second means 10 times itself, and 10 times itself means 10 times 10. That's 100. What's 10 to the third? That means 10 times 10 is 100 times 10 again. That's 1,000. Now I want you to notice something. To the first has 1 0. To the second has 2 zeros. To the third has 3 zeros. And that's what we're trying to get you to notice. Describe the pattern. The pattern is this. The exponent is the same as the number of zeros in the product. And then it says, describe the pattern and use it to evaluate 10 to the 6th without using multiplication. 10 raised to the power of 6 is equal to, and I don't know the number, but what I'm going to do is I'm going to type in a 1 and 1, 2, 3, 4, 5, 6 zeros. Now I do know that. That's 1 million. So I'm going to go back and put my commas in. But how do I know that without doing the math? It's because right here, 10 to the 6 means that you're going to have 1, 2, 3, 4, 5, 6 zeros. That's exactly what it means. So as long as you know the exponent when it comes to tens, then you know the number of zeros in the product. All right, we've got one more, I think. We've got 2 more. I forgot how many we had. All right, we're on 47, and we've done one like this before. Number 47 reads, some numbers can be written as powers of different bases. For example, 81 could be 9 times 9, or 81 could be 9 times 9 and 3 times 3 times 3 times 3. So the way you could write 81 would be 9 squared, or you could write it as 3 to the 4th power. Those both are 81. What we're trying to do is get you to write 64 different ways. So I'll show you how I would do that. I'm going to use a whiteboard here. And it says to write 64 3 different ways, which may be challenging, but we'll figure it out. So 64 could be 8 times 8. So that looks like this, 8 to the second power. Or 64 could look like this, 8 times 8, 4 times 2, and 2 times 2. 2, 2, 2, 4 times 2, and 2 times 2. So this right here, 4 times 2, could break down into 2 times 2. So I'd have 2 times 2 is 4, times 2 is 8. 2 times 2 is 4, times 2 is 8. How many 2's do I have? I have 1, 2, 3, 4, 5, 6. It's 2 to the 6th power. Now if that is like a little confusing to you, let's just check it. Does that work? 2 to the 6th power. 2 to the 6th power means 2 times 2 6 times. So I'm going to count out 6 2's here. And this 2 times 2 is 4, and this 2 times 2 is 4, and this 2 times 2 is 4. And I actually stumbled upon my third answer. It could be 4 times 4 times 4 is 4 to the 3rd power. Now let me check my work real quick. Here's how I can check it. What is 4 times 4? It's 16. And what is 16 times 4? 16 times 4 is 64, which means that this is true. 1, 2, 3, 4, 5, 6. 2 to the 6th power, that equals 64. And 4 to the 3rd power, 4 times 4 is 16, times 4 is 64. All three of these equal 64. Now, all numbers aren't like that. You can't pick other numbers to just have multiple power problems that will work, but 64 is one of them that does. All right, we do have time for this last one, so we're going to squeeze it in. Oman said that it is impossible to raise a number to the power of 2 and get a value less than the original number. Do you agree with Oman and justify your reasoning? We actually did this very similar kind of problem up on number 44. For example, if you had a fraction or a decimal and you raise it to the power of 2, your value actually gets less. For example, 1/2, if that's my base, and I multiply that by 2, what do I get? Well, I get 1 times 1 is 1, and 2 times 2 is 4. And what's greater, half or a fourth? Well, a half might seem smaller because 2 is smaller than 4, but half of a dollar is more than a fourth of a dollar. So my value actually got less. Oman's wrong. Oman is incorrect. If the base is a fraction, or decimal, the product will be less than the base. All right. Great job on page 241. You're done now with lesson 9.1. You can go ahead and take your checkup and your quiz. Good job.